So today what I'm going to talk about is indexing strategy in MongoDB in the first part of today's course. So before talking about indexing strategy, basically these are what we covered in our classes so far. So far in our class, we covered all the basic operations of MySQL and MongoDB. So for the relational database, we used MySQL as an example, and we talked about operations of MySQL. So it's based on the relational database model. So the characteristics is that it is structured, relational, and centralized. So that's the main characteristics of a relational database. And relational database, because it's structured and relational, so we have to do and go through very structured data modeling process using the ER diagram. So we talked about how to do conceptual data modeling. We also talked about how to do relational data modeling. Also, we talked about how to implement database using primary key and foreign key. So those were the main concepts of designing relational database. And then we talked about SQL, structured query language, so that how we can utilize the data stored in the database and how to manipulate those data stored in the database. And then in the second half of the part, we are focusing on the MongoDB. So this is the most popular database system in the NoSQL. So we focused on NoSQL concepts such as unstructured, flexible, and distributed data model. And based on that, we practiced some data modeling in MongoDB. So we talked about document structure, how data is stored in a document format in MongoDB. And also we talked about many different approaches of designing document structure. There could be embedding approach, referencing approach, and in many times we also utilize hybrid approach. So that's what we talked about in our class. Also for the MongoDB query, there are CRUD operation, create, read, update, and delete. So here we talked about query using find function and updating using update function. And also we talked about aggregation last time in the MongoDB. So basically we covered all these basic operations, and what it means is that if you know all this, you are actually able to utilize MySQL and MongoDB without any problem. So as long as you cover all this, there's no problem of using this system and implement something. So all the basic operations of MySQL and MongoDB, now you understand this basic concept, and you also know how to utilize these two systems. And what we are going to talk about today is the advanced use of database system. So you just using the database system is not enough in the real world and in the practice. So by knowing this, you are able to utilize it. But when you utilize it, you want to utilize it better. How to utilize it better is by improving the performance. So that's the most important thing in the big data area. So when we have a lot of data and when we have to process those huge amount of data, our main focus is how to improve the performance. So that's important. And in the database system, usually there are two approaches which many people are utilizing in the practice to increase the performance. One is indexing strategy, another is a scaling strategy. So in the first part of today's course, we are going to talk about the indexing strategy. And later, in the second part of the course, we are going to talk about scaling strategy. So I mentioned about indexing strategy a lot again. And what is indexing exactly? So you can think in this way. Let's say that you have this English dictionary here, and you have to find a certain word. So you want to find a certain word from this English dictionary. And you are not going to scan the entire page from the first page to the last here, because you know that the words embedded in the dictionary, it is already sorted. So it starts from the word starting A and it ends with the word starting with Z. So you know that all the words here in the dictionary are sorted already. So you don't need to scan all the page from the first page to the last page to find the word you want. And also, in addition to this sorting, we have this information here. Like it says A, B, C, G like this. So if you want to find a certain word that starts with alphabet C, then we can just go here and we can only scan this part. So it is much faster. If we don't have an index, if we don't have any sorting mechanism implemented here in this dictionary, finding your word from this huge book will be very slow. But because we have this kind of a mechanism and because we know that the words here are sorted, we are able to find the word we want from this dictionary very easily and very quickly. And we call this as index basically. And in the database system, we have the same index system basically. So indexing in database is support the efficient execution of a query. So when you have an index, it will be much faster to utilize your query. So if you don't have an index, the database needs to scan all the data inside the table and collection. So basically, MySQL has to do table scan and MongoDB has to do a collection scan if there is no index implemented in your system. However, if you have an appropriate index and if you utilize this, it can limit the number of data to be scanned, just like the earlier example of a dictionary. So when you have an index, it will limit the page you need to scan to find your word. It's exactly the same here. If you have an index, it will limit the number of rows of data in the table or documents in the collection to be scanned. So it will be much faster. And in the database system, index uses special data structure. So it will store a small proportion of a data set in an easy to scan form. So basically, you have to choose a certain field to be indexed based on what you want to sort and make an index. You have to determine that. And once you do that, based on the values in this field, based on the values in this field you specified, it will store that value and sort it and keep it separately inside the index. So you can use index to find a certain document you want much faster. So it will allow efficient matching in query operation. So that's the special things what index does in the database system. So indexing will look like this in the database. Basically, it keeps sorted data based on the values of the indexed field. So for index, if you create, it will keep only two things in the database system, the indexed field and data location on the disk. So something like this. Let's just say that this is your MongoDB collection. Then you will have a multiple document. And let's just say that in each document, you have a field called score. And score has a certain value. So in each document, we have a score field. Score field has a certain numerical value. And based on those values, you want to do query. You want to find the document with the score 16, something like that, or score 10, something like that. Then you can create an index based on score field. Then in the score field, the number is stored. So this number will be extracted from each document. So this document has a number 4. This document has a score 7. This document has a score 10 like this. And based on this value, we'll sort. So the smallest score, largest score like this. And it will keep that score information and also a link to the original document. So in the future, if we want to find a document with a score 10, we find this here, score 10, and it has a link. So we follow the link, then there is a document actually stored in our collection. So that's what index does and keeps information in our database system. It keeps indexed field and data location. So if we have an index, how fast our operations can be. So here are some examples. So let's just say that we have a really naive way of having an index. Then we have an index like this, simply a linear format in the linear structure. And we simply have all the score value here sorted like this with the location to the data page, like a document. So if we have an index in this naive way, still it will give you some performance in terms of query operation. So let's just say that you want to find all the data with the score 16. So that's what we want to do. If you don't have an index, what's going to happen is that you have to design a query to check all the documents to see whether score field is 16. Then it will require entire table or collection scan. So if you have n number of documents, then the total scan will be n times. However, if you have an index like this, very naive index, this is sorted. So smallest number is here, largest number is here. Then if we just scan number, we'll look at this number until we find 10. And when the number is bigger than 10, we'll stop here. So here in this case, 16. So we find the 16 here. And if the number is bigger than 16, we stop here. So even in this case, even though the index is made in very naive way in a linear format, we still have to do only 22 scans to find all the documents with the score 16. So 22 means that less than n. We don't need to scan the entire document. We scan until we found the information and we stop here. So on average, if we make an index very naive way like this, total number of scans we have to perform to find the document with the number 16 is still less than n. In the worst case, it will be n like this. But in the most of the cases, in this kind of a database system, we use something called B-Trec data structure. So I'm not going to talk too much details about what is a B-Trec data structure because that's not the focus of our course. That's more of a data structure course in the computer science. So yeah, you asked 23. Actually, yeah, I think the 23 is the right answer in this case. Yeah, that's yeah, that was a good comment. But anyway, yeah, let me come here. So, so I'm not going to talk too much about the B-Trec data structure because it's more of the computer science topic. So in the computer science, there is a data structure course, and they talk about a lot of different data structure. Let me answer to that question a little bit later after this. So most of the times when we create an index, the index will be created based on the B-Trec data structure. So it will be this kind of tree format. So in this case, if we try to find all the documents with the score 16, it will be much faster. So it works like this. First, it starts from the top node. So here we look at this first number. It's 40. It's bigger than 16. Then we go to the left. And we look at 10. It's smaller than 16. So we go to the next one. It's 30. It's bigger than 16. So 16 is between these two, 10 and 30. So we go to the middle node here. And now here we see there's 10. So this is not what we are looking for. Here is 16. So we find document and return it to the user. And the next one is 16. We find it. So we return this document to the user again. And next one, there's no more information here anymore. So we stop here. So in this case, we only need to scan 1, 2, 3, 4, 5, 6 times. So it's very fast. So in this given example, it's 6 times. And they also calculated what will be the average scanning time. And they found that if you use a B-Trec structure with the index, basically the query needs to scan only log n times compared to n times when you do table scan or collection scan. So this is a huge performance increase. So in many of the database systems, they use a B-Trec structure when you create an index. So you can expect that your query will be taking about log n times in the most of the time on average. So one student asked, so we can have an index with the same value, and yes, that's true. So in this case, the score may have the same value like this, 8 and 8, right? That's totally fine. So when you create an index, basically what they do is that they only keep all these values and store it, and they have the link to the original document. So even though it's the same value, the original document is different. So this is fine. Yeah. Okay, so any questions? Okay, if there is no question, let me go to the next one. So that's how the index is working with the B-Trec structure. So what you want to know is this. You don't need to know too much details about the B-Trec structure here. Just know that if you use index, you will get a lot of performance boost. That's the most important part. So indexing is used in many different database systems, not just in MongoDB or NoSQL, also in relational database system. Index has been always there. So in MySQL, it's the same. When you create an index, it's made with a B-tree data structure. And if you use it, it can improve the performance significantly. And in the MySQL, I didn't talk about this when we talk about MySQL, but by default, when you create a table with a primary key and foreign key, these important key, like the primary key and foreign key, are indexed automatically. So actually, you can check in your MySQL. So you can go back to your MySQL and you can check those tables you created before. Then here, for example, in this case, under order system database, there's a customer table. Inside the customer table, we always look at the columns, which field we made before. But below the column, there's this section called index. If you open it, you can see primary key and foreign key are indexed automatically, even though you never made an index for them. So in the relational database, because primary key and foreign key are used quite frequently in the join process when you design a query. So many of the relational database system, when you create a table, primary key and foreign key are indexed automatically so that in the future, when you use join in the SQL, they can perform it fast. So you remember, right? So last time I talked about merge join, so that when you use a join process in the SQL, usually it's not taking that long because they are using merge join. It's because of the index. So they can do join faster. And if you want to make an index by yourself, you can use this comment in the MySQL, for example. You can say create index name on table and field name like this. If you want to remove index, you can use a drop index statement. So I'll skip the details here. In MongoDB, similar, if you make an index, it will be made with a B-tree data structure. Also, it can improve the performance significantly because it's utilizing B-tree structure. And in MongoDB, the ID field will be indexed automatically. That's the automatic way of the MongoDB, and it will be similar to indexing in MySQL. So for example, let's just check it. So if I go to the Robo 3T and if I open TestBA database and open collection, and for example, let's just say that if I look at CD here, collection, and if I open index, you can see that the ID field is already here. If I look at other collection, same ID field is here. So in the MongoDB, ID field is indexed automatically because they are assuming that you may design a query which search document based on ID. So in MongoDB, if you want to create your own index, you can use this function. You can specify database dot collection name dot create index function. And here you can specify the field name you want to make an index on and specify the value 1 or -1. If you put 1, the index will be sorted in ascending order. If you put -1, it will be sorted on descending order, basically. If you want to remove index, you can use drop index function, and you can specify a field and the value 1 or -1, which you used before. Then it will remove the index. So using index without using index, your speed of the operation of the query will be really different. So you can try this by yourself later. So I'll not try this here right now. But basically, I tried running this query here. So my query is this database.restaurant collection. So restaurant collection is what you imported into your database using Mongo import. So you used this restaurant collection for assignment 4 last time. So I use that. So on the restaurant collection, I do aggregation and I use a sort operator and I sort all the documents in the restaurant collection based on borrow information. So based on the neighborhood information, I sort all the documents in an ascending order. That's what I do using this aggregate function. And if I perform this aggregation function in my PC without index, it took about 0.15 seconds. So that's what I had. And later, I created the index by using db.restaurant collection.create index function, and I specify borrow and 1. So I make an index based on the borrow field in each document, and I sorted in an ascending order. So I already have an index which is sorted based on borrow information in each document. So later, when I try this query here, which is sorting all the documents in a restaurant collection based on borrow, then I already have a sorted index. So the query will utilize this index, and simply it will follow the link and give the results to me. So it will be much faster because it doesn't need to sort all the data again. So when I have this index and when I perform this query in MongoDB, the total time it took was only 0.013 seconds. So in this specific case, it's just one example, but you can try many different things. In this specific example, using index made my query about more than 10 times faster, basically. So I was able to get huge speed gain in this case. So when you create an index, you can actually create in many different ways. The most common index will be probably the single index. Basically, it's indexing on a single field. So something like this. In each document, if you have a score field, you make an index on a score field. So that's it, single index. Another type of index, which is quite common, will be compound index. It's indexing on multiple fields. So instead of specifying only one field, you can specify multiple fields. So something like this. You specify user ID and score. So user ID 1, ascending order, score -1, descending order, like this. That's also possible. So if you make a compound index, you have to think about hierarchy on sorting order. So this is very important. So when you specify 2 fields like this, then at first, all the documents in a collection will be sorted by user ID first, because user ID is here at the first level. So all the documents will be sorted based on user ID, AA1, CA2, 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 NB1, XYZ, something like this. And then for each user ID group, basically for those documents with the same user ID, like this here, these 3 documents has the same user ID, CA2. Then among this group, it's sorted again by score. So we want to sort it by score in descending order. So 75, 55, 30, like this. So that's it. So that's the compound index. So you can specify multiple fields, but there will be a hierarchy. It will be sorted first based on the first field, and then it will be sorted based on second field, like this. So when you design a compound index, there is like a slight minor limitation, how many fields you can utilize in given like a different database system. So for example, in MySQL, you can use up to 16 fields, and MongoDB, you can use up to 32 fields like this. So that's another restriction there. So compound index, basically this, you can make a compound index by specifying db.collection name that create index function. And here you can specify multiple fields. So field 1, and how you want to sort 1 or -1. Field 2, how you want to sort 1 or -1. So same here, if you specify db.restaurant.create index and borrow 1, choosing 1, then it will create the compound index. So for example, it's like this. If I show the example really quickly, I have currently this test database here, a test server. Inside the test server, test database, I have this restaurant collection, which I imported last time using the Mongo import. So on the test database, right click on it, and if I click open share, here I can create index. So db.database.restaurants. So on the restaurant collection, if I want to make an index, I can use create index function. And here I can specify borrow 1 and QGen 1 like this. So I want to make a compound index and I want to use borrow as the first hierarchy, QGen as the second hierarchy. So if I click play icon, oh, it's not work. QGen. Try again. Okay, I think there was a connection problem. So now it works. Okay. And then let me right click on the test database and let me click refresh. And if I look at restaurant and if I open this collection, there is index folder. If I open index folder, I can see that here. There's an ID field already indexed automatically. And this new compound index I just created are here. So borrow 1, QGen 1. So based on borrow as the first hierarchy, QGen as the second hierarchy, the index is created. And then what I can do is this. Now I have an index, so I can utilize index. So if I use query, so like on the db.restaurant collection, I make an aggregate function. And in this aggregate function, I can use this. So sort borrow 1, QGen 1, like this. So basically this query is this. I use aggregate function on the restaurant collection. So I sort all the documents based on borrow first. And if it's the same borrow, I sort it based on QGen. So if I perform this query, I think there are some like a connection problem on my PC to the database. Let me try again. Oh, yeah, this is an aggregate function. So I needed to put list. Okay, so if I perform this, yeah, it will be working like this. And then it's all sorted based on the borrow first and QGen second. QGen like this. So you can check it later. So that's how it works. So yeah, so one thing missing is here. So in the slide, yeah, if you look at the slide more carefully, basically after aggregate, I missed this bracket here, right? So I think in this slide, it's all missing because when I made this slide, I was using older version. So that's why. So in the newer version, they changed the syntax a little bit. So that's something you have to be careful when you look at this slide. But anyway, so that's how it works. So when you use a compound index, it's the same. You can get similar boost to Bain, performance boost. So with our compound index, this query sorting took about 0.647 seconds. But after I use index, it was very faster. It took only 0.066 seconds. And also for another query, which use and filtering documents based on the match operator first. So you find the documents in Brooklyn borough first, and then we use group operator to calculate total number of restaurants given each QGen. So in this query, it took about 0.127 seconds without index, but when I use index, it took only 0.025 seconds. So you can see that already there is a performance gain. So let's just think about this. So compound index. So if you create compound index, sometimes your query may use index. Sometimes your query may not use index. So let's just think about those situations when your query will use the index, when your query will not use the index. This is very important because you made the index, but your query is not utilizing your index, then there is no point of making that index. So this is quite important things to consider. So let's assume that we created an index by this example. So we on the restaurant collection, we use the create index function, and we made a compound index based on borrow and QGen as the first and second hierarchy. And index will be, in this case, index will be only used when query follows the same indexed hierarchy. So here, first field is borrow. Second field is QGIN. So if you want to utilize this index, your query should follow same hierarchy. So basically, something like this. In this query, we use borrow, Brooklyn, and QGIN, American, like this. So this is the query on the database on the lesson collection. We want to find the document when borrow is Brooklyn and QGIN is American. So we use borrow as the first level, QGIN as the second level. So in this case, it's consistent with our hierarchy in this index. So when you design this query, which follows the same hierarchy of the fields, it will use index. So you want to check whether your query actually uses index or not, then what you can do is that at the end of the query, you can add this .explain. Then it will explain how your query will be performed in the MongoDB. So for example, here in this case, let's just say that I want to design different query, which is a DB database.restaurant.find function. And here we want to find restaurant in Brooklyn area, and QGIN is American. So you want to find a restaurant in Brooklyn area that serve American food. That's what we want to do. So we designed this query, and we want to know whether this query is utilizing this index we created earlier. Then you can add .explain at the end of the query. And if you perform this, it will show you this result, basically explaining how your query is going to be performed in the MongoDB. So I think someone is using mic. Please turn off the mic if you are not using it, or you want to ask some questions. Okay, so I think it's probably by the mistake. So I muted you. If you want to ask a question, you can write down, or you can turn on mic and ask again. So for now, I just muted it because I think it was turned on by mistake. Okay, so here, so if I perform this, it shows this information here. So you can check whether your query uses index or not. So here there's a query planner. So I can open this. And inside the query planner, there is something called the winning plan here. So if you open winning plan here, there's something called input stage. So if you open input stage, there's another stage here. So here it says IX scan. So IX scan means index scan basically. So here we can know that by looking at this, we are able to know that this query will use index scan. So we are using index. So here you can check IX scan is here. So index scan will be performed. And it also has this information, which index will be used on your query. So on this query, it will use borrow QGIN index because it follows the same hierarchy. So that's how you can check whether index will be used or not. So here same. So in earlier compound index, again, remember that we made borrow as the first hierarchy, QGIN as the second hierarchy. So what if we design a query like this, which only search borrow? In this case, if you put that explain function at the end, and if you check, you will know that it also uses index scan, and it will use this compound index, even though there is only one field here. It's because the hierarchy is still same. So first hierarchy, borrow. There is no other hierarchy. First hierarchy is borrow. Then we'll use index scan. So as long as the first, so when you specify multiple fields, as long as those fields follows the hierarchy from the top, then it will use index scan. So as long as the query follows hierarchy in the index scan will be used. So that's something you have to keep in mind. Then you have performance boost, basically. So this is some example of misuse of compound index. So again, you made a compound index with the first field as borough, second field as cuisine, and you design a query to find the restaurants based on the cuisine like this. Then cuisine is the first level, but first level here is borough, so it's not match. So index will not be used. So based on this query, if you put explain, it says that on the stage on the winning plan, it says collection scan. So MongoDB will scan entire documents in a collection, not using index. This one same. So we want to sort documents based on cuisine and borough. Cuisine is the first level, borough is the second level. It doesn't match with the hierarchy in the index. Then when you put explain function here, then again, on the input stage, you can see that collection scan will be used. So basically index is not utilized in this case. So those are basic information about the compound index. And in MongoDB, there are other indexing features they also provide. Another interesting index you can utilize is a geospatial index. So basically, they support efficient calling of geolocation coordinate data. So if you have a GPS information, longitude or latitude, those number information, then you can use that to create geospatial index. And once you have a geospatial index, you are able to do distance calling. So given a certain location, you can ask MongoDB to find all the restaurants in a certain mile radius, something like that. So distance calling is possible, and more information is here in this link. So you can search more if you are interested in this. And in this class, I will not go too much technical details of this part. Another useful index you can utilize in MongoDB is a text index. So it's very simple and very easy to utilize this. So this also supports efficient searching for string content, basically textual content in a collection. So it's possible in your document, you may have a certain field that contain textual information. Then you are able to utilize those to create a text index. And when you utilize text index, it will only store the root words. What it means is that in your, let's say that you have a text field and this text field contains a sentence or paragraph of the words, basically. And then it will ignore all the stop words, something like the, a, or. So those words that doesn't carry any meaning will be ignored. And also it provides a stemming of the word. So when you have a word like playful, playing, plays, it can be translated into play like this. So it provides some of the natural language processing feature, which is pretty nice. And for the text index, I want to talk a little bit more about this. So how to make a text index is quite simple. So you specify db.collectionName and create index function. And here you specify the field that contains the text value. And here you specify that it is a text. Then this field will be made as a text index. So how to make a text index for all the text fields? So for example, in our city collection, we have a document like this. So we have a street name, which contain text information. We have a borough, which contain text information. We have a cuisine containing text information. We also have a restaurant name that contain text information. So for all these fields, all these textual fields, we want to create a unique one index that is used to search across the name and everything. Then you can use this formula. So you can use create index function and you can specify $sign and star, and then you can specify text. Then basically, this says that all the text fields in your document will be used to create text index. So once you have a text index, you are able to perform a text query. So you can specify database, collection name, find function, and you can specify text operator, you can specify search operator, you can specify the value you want to search. So using this, you can provide a search functionality to the user very easily because everything is here. So for example, in my database here, I can create a text index by using db.restaurants create index and $* and I want to make a text index. So I can type this. Basically, what I'm talking here is that for all the text fields in my document, I want to create a text index. So type this. If I click play icon to perform this, it will take a little bit time, but it's done. And now if I refresh test database, and if I look at restaurant collection and look at index, I can see that text index here is created. So once I have a text index like this, I can perform text search. So on the db.restaurant collection, I want to find restaurant that contains Flatbush, for example, this word. And I can design this query here. And if I perform this, here is the answer. So if I look at this, it contains here Flatbush in the name. So it's searched here. Second one here, best walk Flatbush again on the name. And third one here, Flatbush Halal restaurant. And the next one here, this one doesn't have a Flatbush on name, borough, cuisine. But if I open address, it's on Flatbush Avenue like this. So this kind of implementing this kind of like a search functionality might be cumbersome in some other like tools, but in MongoDB you can design this kind of a search functionality based on a certain word very easily by using text index. So that's what I wanted to show here. Okay, so basically that's all about the index, how to create index, how to utilize it, and what's the something to be careful. And another thing is the design issue. So the general rule is this: if you use index, it will improve performance. So that's for sure. When you have an index, and if your query utilize that index, it will be faster. However, you have to be careful about this. The misuse of index will slow down performance. That is also possible. So what I mean is this: we know that index will increase the performance. Then one may think that, why don't we just make an index on every field? So on restaurant collection, we make an index on borough, index on cuisine, index on name, index on restaurant ID, index on address, the building, like this. For every field, we make an index. Then you may think that it will be very fast. But that's actually a problem. And in the real world, some people actually make this kind of problem quite often. So this is the story that I captured from one of the programming website. And this person who posted this story was a consultant who are into optimizing the database performance. So he was helping a client who said that there was a problem in his database, and in his database, the speed is very slow. So he was complaining about this, and this consultant went to him and tried to look at what's the problem. And basically he's saying this. So recently he helped the customer to optimize his database. He found that there's a write log on the database was running consistently at 95%. And CPU was spiking constantly and making for a poor experience. We looked at the index and determined the customer had too many index. So the customer had 126 non-ID index. So non-ID index means that in addition to those of index made automatically, this customer made 126 customized index basically. And he also found that there are 24 index on one collection in MongoDB. So for each insert, update, that modify key, MongoDB was having to insert the document and update the 24 index. And this was the cause of the excessive write log. So here, what it means is this. So there are some words like write log. So write log is this. So when database is here, so let's say that this is MongoDB server and we have some collection. So in the collection, we have multiple documents. And in MongoDB, what's happening is that when you update a certain document, so it's not just MongoDB, when you update a certain information in a collection or a table, the index should be updated together. And while index is being updated, the database system limits another update. So while index is being updated, another update request should wait first, because index should be updated first, and then it can receive another update request to the database system on the same collection. So what's happening here is this. This person, in one collection, there are 24 index. So when a new document is inserted, or when an existing document is updated, the MongoDB has to make sure index is correct. So think about it. So you already have index, but the index by definition, it should be sorted. It's the sorted information. So when a new document is added, we have to find where to put this new document in this index. So this index needs to be checked again and should be updated. And the problem is that if you have 24 index in one collection, when a new just one document is added, these all 24 index should be also updated together. And that's the problem here. So when you create too many index on one collection or one table, you have to think that whenever there is an update, all these index also need to be updated. And that will make the process slower if you are expecting a certain amount of updates in your system. So the thing is this, index definitely increase the query performance for read operation and sorting operation. When you retrieve data from the collection or table, if you have an index, if you utilize it, it will increase performance. However, having index means that inserting cost will also increase. For every new document you add into a collection, all the index need to be updated. So that's the problem. So there's a trade-off between query performance, like a read operation, and inserting performance. So that's something you have to be really careful when you design and utilizing index in your system. So actually many people in the practice, I think in the industry, they are talking about this issue. So people say that, does index really slow down insert MySQL? So even in MySQL, when you use index, the insert performance will decrease. So that's obvious. And also another person say that after creating index in MongoDB, write operation is taking too much time. And that's kind of obvious because whenever you have a write operation coming to the MongoDB, it has to update the index again. So you have to already think about this. There will be always trade-off between read and write. So if you want to increase the read operation speed, you have to sacrifice write operation speed. So in your online service and in your online system in the future, like if you're working in a company or if you are really dealing with this kind of system, you have to think about these two things. How many read operation should be performed? How many write operation should be handled? And you have to make a balance between these two. So that's a kind of important things you have to think from this example. So indexing strategy, if I summarize, basically you have to understand your queries very well, and you have to think about which queries will be used quite often in your system. So you have to think about what will be used for matching operator criteria. So if a certain field is used a lot in the matching operator, so for example, if a certain field is used a lot in the query operation, you have to create an index for that part. But if some operations will not be performed a lot, then you don't need to make an index for that field. Also, make sure that you limit the number of index in a collection. If you have too many index in a collection, then definitely the performance will be affected. the reason is this. So one student asked why all the indexes should be updated. It's because of the B-tree structure. So I didn't go too much details about data structure in this course. So I not talk too much details about technical details about the data structure. But earlier what I mentioned is this, right? So when we make an index, and most of the database system will use a B-tree data structure. It's because B-tree data structure will provide very fast read performance. It's just log n times, so it's very fast. And this B-tree data structure, when a new data is inserted, keeping this tree structure is very complex. So I'm not gonna go too much details about this because it's kind of another topic. But basically, when a new data comes, then we have to look at the position for this new data. Should it be here, or here, or here, or here, or here, something like this. And we cannot keep adding. So let's say that we want to add 10, for example, then we'll add 10 here. Then let's just say that there are a lot of documents with a score 10. Then we'll keep adding here. Then only this node will be very bigger. Then if only one node is very bigger, if the tree structure is not balanced, then the performance, the average performance will not be log n. So we have to change the tree structure. So we have to divide node. We have to make more edge, more branch, and sometimes we have to increase the depth of the tree. So there are a lot of complex restructuring of the tree is going on to maintain this B-tree structure. So that's why. So it's not like a very simple. So it's not like a, it's not like we can just add one data point here. So that's why this kind of thing is happening. So basically, having B-tree structure, we are assuming that we are going to give up write performance for the read performance. So we are already having that mindset in the database system. So I hope that answers to your questions. And then the last point is this. It's also good to ensure that your index will fit in a RAM. So in a collection, when you're working on it, sometimes you will create a multiple index. Then you have the working data set and you have some index for a certain field. You have some index for a certain field. You have some index for a certain field like this. That's totally possible. And this index size, it is good to be fit in your RAM size in your server. Because if it doesn't fit all here, then some of the parts will be saved not inside RAM, but also outside RAM, like in your disk storage. Then that can slow down the process. But that sometimes it's unavoidable because when you work with the data, index and working set will keep getting bigger and bigger. And sometimes index will keep getting bigger as the data size gets bigger. That's kind of naturally happening. And at a certain point, if your index and working sets are too bigger, so it cannot be stored in one RAM storage, what's happening is that the leftover, the rest will be stored in the disk storage. So when a certain part of index is being scanned, it will be loaded here, and the rest will be here. And when we request the next part of index, it will be loaded back here, and this part will be saved back into the disk storage. So we call this as a swap in the computer science. And if there are more swaps, the performance becomes slower. So another key point is that you also have to think that the index size should not be too big. If you have a too big index, so for example, if you make an index based on really huge field, that will also slow down the performance. So that's another technical point. You have to be careful when you are utilizing index.